we're going to be continuing our discussion on analyzing building energy use. So this is the part 2 of the last lecture. I think this one does run a little bit shorter, thankfully. So why do we do this? Well, one big reason for looking at weather dependency. So last class we looked at taking build energy use in electricity and gas, and how do we calculate heating and cooling degree days, and then looking at the dependency between those two things. And so one reason we're going to look at that dependency is to compare the before and after usage for any energy saving projects that we do. First, we have to define some generic or general terms. The first term is what's called the baseline year. So the baseline is the period before the energy project. So before we've done anything to help them save energy, that's the baseline condition. The baseline year would be that overall period. So say the year before we did anything, how much energy did they use? The year plus 1 would be the period after you do the energy project. So you do the energy project, and then you can look at the bills a year later, year plus 1. So that would be that period. And if you're going to do a project that saves energy, you expect, or you would hope, that you would be able to see that on the utility bills. At the end of the day, some clients don't really pay attention, but some of them do. And we've had many customers call us, and they've done their own bill analysis. And then they call us up and say, hey, it doesn't look like we're saving the amount of energy you said we would save. What's going on here? As an example, so let's say you have an energy project estimated to save 50,000 therms in a year. And then you look at the bills for the following year, that year plus 1 period, and they show that they only saved 42,000 therms compared to the previous year. Does that mean the project didn't live up to expectations? Well, we don't have all the information necessary here. So what if you did some rough weather analysis and you found out in that baseline year they had 4,000 heating degree days, and in the year after they had a much colder winter and they had 4,800 heating degree days. So they had about a 20% increase in severity in how cold that winter was. And so based on that, you would expect that year after to use more heating energy. And so that will play a role in how these savings are determined and expressed. So maybe they still saved energy, but they just didn't save as much. Well, how much of that is due to the weather, and how much of it might be due to the energy project just not performing as well as you expected? So to make a apples to apples comparison, we have to do what's called weather normalizing the data. We touched on this in the last class, where you plot your electric and your gas use against your heating and cooling degree days, and you run that linear regression. So we're going to expand on this idea. So you do that linear regression, you come up with those equations that will give you a way to predict energy use. So you're going to come up with one equation that says, I can predict monthly kilowatt hours based on a certain kilowatt hours per cooling degree day times cooling degree days for that month, plus some base kilowatt hours. Similar approach on the gas. You'll have some base therm use every single month, and then you'll have increased therm use per heating degree day. And really, both of these equations follow that general y equals mx plus b format. So you have your slope, your variable, and your intercept. So that intercept b term, that is some base usage that they're going to use every single month, regardless of how cold or warm that month was. And then that slope value represents some added use based on how severe the weather was. So this is just kind of reviewing what we talked about last time. So from last lecture, we had this chart. So there's our equation. So we have an intercept of 61 therms. So they'll use about 61 therms every month. And then they'll use an additional 1.5 therms for every heating degree days in that month. So now that we have these equations, we can estimate what the usage would have been given a different set of weather data. So again, back to terms, our baseline, that is based on actual usage and actual weather data. So that's our how much electricity did they use, how much gas did they use, and what was the actual weather data over that period. And we're going to use that to generate those building signature equations. And then we have this new term that generically we call baseline plus one. And this is defined as what would the usage have been the following year, assuming they didn't do an energy project. And so this is entirely theoretical, a theoretical usage. So you've done the energy project, now you're a year later, and now you're going to kind of look back and think, what would they have used had we not done that project based on that weather data from the following year? And then the year plus one, which is our post project or post retrofit data, which this is again actual usage and actual weather data for that following year. So the baseline and the year plus one, those are based on actual data, actual weather data, actual usage and actual weather data. The baseline plus one is that theoretical scenario had we done nothing. You perform that linear regression on your baseline data, then you take your actual year plus one weather data to estimate that baseline plus one usage. And I'll have an example here to help illustrate this. And then to come up with your actual savings, you take your baseline plus one use minus your year plus one use. So that's a lot to take in. So let's run through an example. A customer comes to you. They say, hey, we've looked at our bills and we're just not saving what you said we would save. And here's the information they give you. So here's what they started with: about 1.7 million kilowatt hours, 124,000 therms. And then they looked at their bills a year later, a year after the project, and you can see we made some pretty good savings here. And so the what I call the raw calculated savings, or the non-normalized savings, which is just the delta between the two. So the customer just took the before and after, and this is what they came up with. So the original savings that we estimated them, that we said they would save, is 240,000 kilowatt hours and 18,000 therms. So what this means is the way the customer's looking at this, they are underperforming. So there are still savings there, but it's not as much as they were expecting and that we calculated and told them they would save. So were the savings not right? Did we do our calculations wrong? Well, the first step is to look at the weather. So let's say you pull up the weather data off of the website I showed you last time. During that baseline year, that's the heating and cooling degree days. And then in year +1, so the year after the project, we had more cooling degree days, more heating degree days, and not necessarily by a small amount. So we expect year +1, they're going to use a little more energy just because the weather was more severe. But how much more? So we do that linear regression on the baseline usage and the weather data. We get those equations. Now we can use those to predict usage given some new degree day data set, namely this year +1 right here. And then now we can estimate what would the usage have been that following year had we done nothing. So if this is their electric use and associated cooling degree days at 60 degrees balance point, so you can see, as expected, you get a bump in cooling degree days in the summer months, and then in the winter, it trails to 0. On the heating side, you have the opposite, where you have a lot more heating degree days in the winter months, and then essentially no heating degree days in the summer. So that's as expected. And now we perform that linear regression on both of these data sets, generate that trend line, get our equations. On the electric side, there's our equation, r squared 0.78, 0.79, not bad. We'll talk more about that here in a bit. On the gas side, we can see increased gas use for increased heating degree days. We have our equation here where we can predict gas use. Pretty good r squared there. So after we do that, we have our equations. So on the electric side, this will translate into 128 kilowatt hours per degree day, plus that 129,000 base use. On the gas side, translates to 26.6 therms per heating degree day, plus 600 therms base use. And now we take our new weather data from the year after, and we plug that into those equations. And now we have what we call a weather normalized baseline. So we've essentially taken our baseline building and transported it into the future to create this theoretical model. You sum the totals, and then your savings will be your weather normalized baseline minus your actual use in that year +1. And again, that part is theoretical, that part is actual. So here's our actual baseline use and associated heating and cooling degree days. And then if we run through those steps, we get this estimated baseline +1 use. So on the electric side, they used 1,675,000 kilowatt hours, but theoretically they would have used a little over 1.7 million because of that increased cooling degree days in that year. On the heating side, we started at around 124,000 therms, but because of the increased heating degree days, that puts us at 129,000. So now in this theoretical elevated, weather normalized baseline, now we can actually compare apples to apples because we're using the same weather data sets. And then you take your actual year +1 use. And so you can see in these two scenarios, we're using the same degree day data. And then those are the two scenarios from which you're going to calculate your savings. So if we look at the electric savings, we take that weather normalized baseline and subtract the actual year plus one use. We come up with about 258,000 kilowatt hours. Similar approach on the gas side. Weather normalized baseline, 129,000 therms minus the actual year plus one use. We come up with a little over 20,000 therms. And so now we have the weather normalized savings. And now we can go back to the customer and show, hey, we actually overperformed. You would have spent X amount of dollars had you done nothing, but you saved more than we thought you would. So now you can turn the story around from the customer thinking these people don't know what they're doing to, oh, hey, yeah, that makes sense. We're actually doing great. We're doing better than expected. And usually customers understand that, hey, we had a warmer summer or a colder winter. I mean, that's an easy way to justify how that's going to impact their usage and their savings. So that's a lot. Any questions before I keep moving on? Cool. You're all experts. Some pitfalls, though, to watch out for when you're doing this kind of analysis. When you come up with those equations, those building signature equations to predict energy use, it's not exact. It does do pretty good when you're looking at a larger data set. I would say at minimum, you want at least a full year of data to work with. If you look at it on a month-to-month basis, that's where things start to get a little screwy. So generally speaking, you don't want to do that to estimate the monthly savings. So in that previous example, if we looked at June of this year to June of last year using those signature equations, it might not look good. And by looking at the full year, really that just allows some of the variabilities and unknowns to kind of be smoothed out. If you look at it month to month, it just doesn't work. Or if it does work, it's just a coincidence. You really need at least a full year for this data to kind of average out. What we've been looking at with pairing kilowatt hours to cooling degree days and therms to heating degree days, that is a single variable regression. You only have one variable for each of those that you're having to worry about. On the cooling side, you're saying the only thing impacting electric use is cooling degree days. And similarly for gas use and heating degree days. Weather dependency, that is the most common thing that we're going to compare energy use to, but we can have other variables. So if you were to look at a hotel, how many rooms were rented? That's going to have a definite impact. Weather will still have an impact. So in a hotel, now you have two variables that you need to account for. Or in manufacturing, how many items did they make month to month? And again, weather can still impact that use, but now you have this other variable that gets thrown into the mix. And so that's how we arrive at what we call multi-variable regression. And so this is still a regression analysis, but what this will do is allow us to account for weather and any other factors simultaneously. Most commonly, what I see, especially in rural Washington where they may not have gas service, because their electricity is so cheap. What if your building has electric resistance heating and air conditioning? So now in the winter months, your electric use is going to go up because you have electric heating. And in the summer, your electric use is also going to go up because you have air conditioning. And so now you have two variables for one output of your electric use. So here is an actual building. Um, Actually, I did my my capstone project on this building for my master's degree. So it's this is an example of a building that has electric heat and air conditioning. And so plotted on this graph, the green line is our kilowatt hours, the red line is our heating degree days, blue line is our cooling degree days. And you can see as the heating degree days go up in the winter months on both sides of this chart, you see a corresponding increase in electric use, which makes sense because they have electric heat at this building. And in the summer months, you can see when cooling degree days go up, the kilowatt hours also go up. In this case, it's only a very slight bump. Normally this hump in the summer is a lot more pronounced, but in this case it wasn't. So now I want to do a multivariable regression analysis. I want to be able to predict how much electricity am I going to use based on two variables, heating and cooling degree days. So if that's my data, in this case, I used 2 years of electric use to really nail down the analysis. So that would be the output I want. I want to be able to predict my electric use. There are my heating and cooling degree days, assuming a 60-degree balance point for those 2 years. And now when I run a multivariable regression on this in Excel, which I'll show you how to do, this is what it spits out. And you may look at that and your eyes glaze over, don't even want to process it. You don't have to understand everything on here. If you're a big statistician nerd, then have at it. But let's identify some of the things that we care about. The cell at the top, when you're doing the analysis, you need to tell it where to output the data. So wherever you click to output, that is that cell right there. That's where it will start. You need to be concerned about the R-square and the adjusted R-squared values, the significance F, and I'll go over what all this means here in a moment. Down here, the headers get transferred here. So the fact that I labeled these variables, heating degree day 60, cooling degree day 60, it will transfer those headers to here. These are your equation coefficients. And so this is what I can actually use to generate my my predicting equation. So I would read this as my monthly kWh will be equal to about 29,000. That's your base use. Regardless of whether that building is using about 29,000 kilowatt hours. And then we have an additional 20.4 kilowatt hours per heating degree day and an additional 6.2 per cooling degree day. So now I have two variables in my equation. And then we have what are called the p-values. So what does all this mean? The R-squared, this is probably the only one you've heard of. And generally speaking, people like to define R-squared as how well does the data fit the regression equation that was generated. A more accurate description is how predictably does a variable change the output. So if we're using variables of heating and cooling degree days, how consistent and predictable are those variables changing my output? That's a more accurate statement for what R squared means. This is always between 0 and 1. 1 would be an absolute perfect fit, and you only have one value for this entire data set. Generally, the goal is to be above 0.8. Higher is better. The issue, though, specific with a multivariable regression, the regular R square value is always going to increase anytime we are adding predictors and variables, even if they are just absolute crap. I don't know why this is. Again, you'd have to get the statisticians on the phone to ask them. But for some reason, if you add more variables to the analysis, even if they're bad variables, it will increase the R squared. And so that can lead you to some wrong conclusions, which brings us to the adjusted R squared. And like its name implies, this adjusts the R squared to penalize for any variables that you added that ended up not being a good predictor. So if you thought, well, maybe the energy use is tied to this other thing going on over here, and you add that variable in, but it's not a good fit, that will bring down the adjusted R squared. If it is a good predictor, then the adjusted R squared will still be nice and high. But ultimately, this is always going to be less than the regular R square value. It can even be negative if your regular R square is really low. If it goes negative, you're probably not dealing with a very good data set, or you're really adding in variables that you have no business adding. The goal here, still, we want to keep it above 0.8. Higher is better. And if you're doing a multivariable regression, this is a better metric than the plain R square. I don't even look at the R square in a multivariable regression. So the next one is what's called the p-value. And this may be a little conceptually hard to wrap your head around, but the p-value is the statistical chance that a single variable is not affecting the output. So they kind of flip it on its head a little bit, where they're saying, what's the chance that it's not affecting the output? And every p-value, every variable that you put into the analysis gets an associated p-value. And the goal here is to be nice and low, generally below 0.05. So if one of your p-values was 0.05 on one of your variables, that would say there's a 5% chance that this variable is not affecting the output. Whereas we want it to affect the output. So that's why a lower value is better. And you have multiple p-values because you have one for every variable you throw in to the analysis. Similarly, the significance F value, same concept, except this is looking at the overall group. So what's the statistical chance that a group of variables is not affecting the output? And so here you have one significance F value for the entire data set. Again, you want it below 0.05, lower is better. So now let's look back at that analysis. So the R square and the adjusted R square, they are both well above 0.8. So that gives me pretty good confidence in the variables that I've put in here. Significance F. So this is looking at the variables as a group. So we're looking at heating and cooling degree days. And what's the chance that those variables as a group are not affecting the input? Well, 5.95 to the negative 12th power, that's a pretty low value. It's extremely low. So that gives me high confidence that I can predict the usage based on those variables. And then the p-values, which we have one for each variable and actually one for the intercept as well. That intercept p-value, 1.74 times 10 to the negative 18, extremely low. Heating degree day 60, also extremely low. So that tells me there's very high confidence in these two values here, that they can reliably be used to predict electric usage. But then you get to this cooling degree day variable. So 0.13. Well, that's above our 0.05 threshold where we kind of want to be. Sometimes the data doesn't always fit the way we want though. So this is saying, hey, the cooling degree day variable, that seems to be predicting the use, but there's a 13% chance that it's not, that it's just a coincidence that it seems to be predicting the use, but it's really not. 0.13, that's not terrible, but not exactly where we want to be in an ideal situation. Looking back at that usage plotted against the heating and cooling degree days, it makes a lot of sense that the p-value for cooling degree days is high, which is not what we want, because there is only a slight correlation here. We do see a slight bump in electric use based on the cooling degree days, but it's only a very slight increase. And so that helps support this idea that, well, maybe the cooling degree days aren't that great at predicting use. But on the flip side, it makes sense that the p-value for heating degree days is very, very low, which is good because there is a strong correlation there. You can very clearly see as my heating degree days go up, my electric use also goes up. So that makes sense with what our analysis has told us. And if you got into a very complex analysis with 4 or 5 variables, this can get very, very complicated. And in that scenario, what you might have to do is run, say, one analysis where you include all 5 variables, and then maybe you run it again, but you exclude one of the variables and see if that might fit a little better. And so it becomes a trial and error kind of analysis. So my explanation of all this stuff is, this is like high level. This is how I understand it as an engineer kind of explanation. If you have any friends who are, or if you are very into statistics, you probably wouldn't be happy with the way I just explained those. But from my perspective, the way I just ran you through those metrics should be good enough. So let's say you run through that analysis, but then what if your data changes? You have to rerun that analysis again, running through the same steps, which I'll show you how it's done. Some useful Excel functions. If you're going to generate your building equations, the kilowatt hours and therm equations, well, one way to do that is you just graph the usage and then generate a trend line on the graph, and then that spits out your equation. For me, I think it's a better idea to use Excel functions to generate these terms, which I think I mentioned these in another class, but slope, intercept, r². The advantage of using these functions is this will auto update for changing data. So if you plug in new y values, new x values, these functions will spit out new slopes, intercepts, r². These only work for single variable regression though. But the important thing is it does auto update if you change the data. When you're doing multivariable regression, it is possible to generate these terms, your coefficient terms in your equation, your intercept and your cooling degree day coefficient and your heating degree day coefficient. It is possible to generate those terms live. I put that in quotes, live, or to say auto update based on changing data. It's a lot more complicated, and I honestly I don't think it's worth getting into. So let's go through a quick example. And then I'll let you get out of here. Okay, can you see this okay?
Yes. Yeah, we see it.
Okay. So the first thing you need to do to run a multivariable regression, which I won't read through all this, but when you look at the slides on Blackboard, here's all the steps to enable this. So if we open Excel and you go to File, Options, and then Add-ins, then we need to go down here where it says Manage Excel Add-ins, Go. It brings up this add-ins deal, and you check that box, Analysis Toolpack. Click OK, and now you should be good to go. What you need to do, so this is that same data we were just looking at in that example. So we have our electric use, demand, electric cost, gas use, gas cost, some tabulations over here. We calculate things like EUI, cost index. We've talked about both of those. And then we have our weather data. So if you go up to the ribbon and you go up to data, all the way to the right here, this will now show up. So you click data analysis. You look through this big list of things you can do. You find regression. Click OK. And then it brings up this dialog box. So we need to input our Y range. So we are trying to predict the electric usage or kilowatt hours. So it already, here, I'll delete this out, start from scratch. So our Y range will be our kilowatt hours. So you select that range. Our X range, so this will be all of the variables that we want to include in our analysis. In this case, heating and cooling degree days. And these have to be right next to each other so that you can grab them both in one box. The output range, so this is where do you want Excel to paste the data? So let's just throw it over here. Just select one cell. And let's leave all of these other boxes unchecked for now. You click OK. And then here is all of that data. So now you have this data to work with. But the problem is these are all just hard numbers. So if I change the data over to the left, that won't update anything over here. I would have to change the data and then rerun the analysis. So one thing I did do, that's always a bad idea. So you notice here, that Excel auto-named my variables, X variable 1 and X variable 2. Well, one of those is heating degree days and one is cooling degree days. Which one is which? I don't know. So the way to fix that, if you run your analysis again, so it brings up the dialog box. Now for our Y and X range, we're going to include that header above it on both of these. So now include those headers right there. And then what you need to do is click this labels box. And now this tells the analysis program, hey, the top cells, that's my header. That's my label. That's what I want you to call my variables. And so now when we click OK, it will say, hey, we're going to overwrite all your data. OK. And now you can see that it actually labeled my variables heating degree days and cooling degree days. So that's multivariable regression. That's all I got today. Any questions before you head out? I'm happy to stick around too if there are any homework questions. Got you out a little early this time. All right, no questions. So I'll hang out if anybody wants to keep working on homework or anything in the background. So yeah, feel free to head out though. Thanks.
Thank you.
Thank you.